Today we will discuss the HMM and its algorithmic aspects. We have seen that HMM is a very critical machine, a very useful machine for statistical natural language processing, and our goal would be to understand the algorithmic aspects of this machine. We remark that there are three important problems that are solved by hidden Markov model. The first is that we would like to compute efficiently the probability of the observation sequence. The next problem, which is the most important, is that we would like to compute the probability of the state sequence, the best possible state sequence given the observation sequence. So, we would like to find out the best possible state sequence given the observation sequence, and the meaning of best possible here is the sequence has the highest probability given the observation sequence. And the third problem is to find out the transition and observation probabilities or the parameters of the hidden Markov model given the output sequence or the observation sequence which are accepted by the machine or generated by the machine. So, we concentrate on the second problem now to find out the best possible state sequence in terms of highest probability value given the observation sequence. So, we first start with this particular diagram, which we call a probabilistic finite state machine. This is nothing but the hidden Markov machine of order k equal to 1. That is why we can draw this kind of states with only one state symbol in it, S1 going to S2 on symbol A2. If I look at this arc, for example, this means that the probability of going to state S2 with output symbol A2 is 0.4. So, this you would remember is a very definite probability. We look at the paper and I have written it for you. The paper shows the meaning of the probability of A2 being 0.4 on the arc going from S1 to S2. The meaning of this probability value is PA2 comma S2 given S1 is 0.4. Now, this particular probability can be written as PA2 given S1 into PS2 given S1, which is equal to 0.4. And the next probability, that is PS2 given S1, the second probability expression, makes this as independence assumption that the probability of a state depends only on the previous state and nothing else. So, the meaning of this particular picture is probability of A2 given S1 into probability of S2 given S1. So, going back to the slides, we have this machine with us, and the question that is being asked is, what is the most likely state sequence given the output seen? We will take a particular output sequence which is A1 A2 A1 A2. Okay, our output sequence will be A1 A2 A1 A2. Now, we would like to predict the best possible state sequence corresponding to this observation sequence. So, we are going to find out the best possible state sequence in terms of S1 and S2 given the observation sequence A1 A2. All right. So, here is the tree which clearly depicts what we have to do. So, initially the system is in the start state, and from there with probability 1.0 it goes to state S1, and with probability 0.0 it goes to S2, which means the machine starts from state S1. The next symbol is A1. When A1 comes in, then from S2 we go to S1 with probability 0.2, from S2 to S2 with probability 0.3. So, this is as per the finite state machine which was shown before with probability values on it. Now, what will happen is that these probability will get multiplied by 0, and therefore, the probability of the state sequence S2 S1 and S2 S2 will be equal to 0. So, we did not consider these probabilities and these nodes anymore. There is no point advancing these nodes. They will always get multiplied by 0 and the probability value will be 0. So, we concentrate on this part of the tree, and from S1 here on A1 we see that the probability of the state transition from S1 to S1 is 0.1 on A1, S1 to S2 is 0.3 on A1. The probability of the sequence S1 S1 on the observation sequence epsilon A1 is 1 into 0.1, which is the product of these probabilities, and sequence probability here is 0.3. So, S1 S2 sequence probability given the observation sequence epsilon A1 is 0.3, and the sequence probability of S1 S1 is 0.1. Next symbol that comes in is A2. Here we advance the node here S1 to S1 and S2. This node S2 is also advanced to S1 and S2. The probability values on these arcs are 0.2, 0.4, 0.3 and 0.2, meaning thereby S1 on A2 goes to S1 with probability 0.2, S1 on A2 goes to S2 with probability 0.4, S2 to S1 is 0.3, S2 to S2 is 0.2. This we have seen before in the probabilistic finite state machine. Now, when we look at the sequence S1, 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 the probability of that comes out to be equal to 0.1, which is the accumulated probability of the subsequence S1, S1 into the transition probability, which is 0.2 on A2, and the probability value now becomes 0.1 into 0.2, which is 0.02. So, the probability of the sequence S1, S1, S1 on A1, A2 is 0.02. Similarly, the probability of the sequence S1, S1, S2 on observation sequence A1, A2 is 0.04. That of S1, S2, S1 is 0.09, that of S1, S2, S2 is 0.06. Now, it is quite easy to see that what we have been doing is correct. We will do a slight amount of mathematical calculation to show that our theory is fine as far as doing this mathematical task is concerned. So, we are saying that we would like to compute the probability of S1, S1, S1 given the sequence epsilon A1, A2. Now, by chain rule, this is probability by Bayes theorem and chain rule and Markov assumption. We get this as P epsilon A1, A2 given S1, S1, S1 into probability of S1, 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 and the denominator is probability epsilon A1, A2. So, this denominator is not computed, because these probability values are used for comparison, and they are not used because the denominator is same for all the nodes which are compared. So, this will be equal to probability of A1 on S1 into probability of A2 on S1 into probability of S1 on S1 into probability of S1 on S1. Okay. And that is equal to probability of S1 on S1 on A1 into probability of S1 to S1 on A2. So, we can take the product of these two probabilities and compute the probability of the sequence. This is due to the application of Bayes theorem, chain rule and Markov assumption. So, looking at the slide once again, we see that the sequence probability can be found out simply by multiplying the transition probability with the accumulated probability so far. Now, when we do this and when we have got these 4 children ending in S1, S2, S1, S2, then we compare those sequences which end in the same state. So, sequences ending in S1 are S1, S1, S1 and S1, S2, S1. The probability of S1, S2, S1 is 0.09, that of S1, S1, S1 is 0.02. Now, we observe that the children of this S1 will never be able to win over the children of S1 coming from here. So, this again we can illustrate by writing. So, we have an S1 here and the sequence is S1, S1 and another S1 here, the sequence is S2, S1. So, S1, S2, S1 and the accumulated probability here is 0.02, accumulated probability here is 0.09. Okay. So, the probability of the sequence S1, S1, S1 is 0.02, probability of the sequence S1 is to S1 is 0.09. So, this is equal to P S1, S1, S1 given A1, A2 and this is equal to P S1, S2, S1 given A1, A2. Now, when the next symbol comes, which is A1, we will be advancing these states. This will be S1, S2, S1, S2 and the values here will be multiplied by the transition probabilities. Okay. And now, we see that we are always multiplying by the same quantity for a same state transition. And when this happens, this node will always be less than this node. The accumulated probability here will be more than the accumulated probability here. Similarly, the accumulated probability here will be more than the accumulated probability here. Therefore, the children of these node will never be able to win over the children of this node. Okay. Therefore, there is no point advancing this node and we cancel this out. So, when we cancel this out, we look at the slides once again. Here this S1 need not be advanced anymore, we have to advance this S1, this S2 need not be advanced anymore, we have to advance this S2. So, going to the next slide, we have this S1 and S2 with their accumulated probabilities 0.09 and 0.06. Now, the next symbol comes in, which is A1. The transition probabilities are as shown here 0.1, 0.3, 0.2, 0.3. Accumulated probability is multiplied by these transition probabilities. The new accumulated probabilities are 0.009, 0.027, 0.012 and 0.018, which is the product of previous accumulated probability and the transition probability. All right. So, now, when we look at the sequences ending in the same state. So, here is this sequence ending in S1. Sequence ending in S1 here has higher probability than the sequence ending in S1 here. Okay. Therefore, we retain this node and discard this node. Similarly, this node S2 with probability 0.27, which is more than 0.018 is retained, the other node is discarded. And we find that now we have S2 and S1 here. The next symbol is A2. When A2 is presented or when A2 is output, then the sequence that results is ending in S1, S2, S1, S2 with at these 4 nodes, and this particular node has the highest probability of 0.0081. Therefore, this is the winner node, and when we work backwards, we can recover the state sequence which has the highest probability corresponding to the observation sequence A1, A2, A1, A2. So, the winner sequence would be S1, S1, S2, S1, S2, S1. So, S1, S2, S1, S2, S1 is the winner sequence, and this is the best possible state as far as the output observation sequence is concerned. Now, this particular algorithm is known as the Viterbi algorithm. This is known as the Viterbi algorithm. Okay. This is used for predicting the state sequence given the observation sequence. Very efficient algorithm. Time complexity is equal to number of states into observation length. So, number of states into length of observation. This is the complexity. So, how is the complexity number of states into length of observation? So, let us see what is going on in the way the algorithm proceeds. So, we have seen that initially when the first symbol is obtained, we have two states coming out from S1 at S1 and S2. When we have the next symbol, then both S1 and S2 produce 2 children each, but only 2 out of these 4 are retained, other 2 are discarded. So, if there are k states in the machine, then at every level we retain k states, okay, we retain k states and we discard the others. Okay. And that is done by noting all those sequences which end in the same state and retaining that sequence whose probability is the highest. So, at every level we retain exactly k states and the number of levels is equal to length of the observation sequence. So, number of states into length of observation sequence is the complexity of the algorithm. If we were advancing all states, okay, at every level, then you can see the complexity would be number of states to the power length of the observation sequence. So, because of the Markov assumption, because of the fact that a state depends only on the previous state, we are able to bring down the complexity from exponential to linear in the length of the observation sequence. So, there is a tremendous amount of saving and that is possible because of dynamic programming. The way the algorithm works is that it makes use of the accumulated probability seen so far. So, this is the way the algorithm works and the tree based discussion makes it quite lucid. Next, we show a tabular representation of the tree, which is very useful for computational implementation of the algorithm. Here is a table which is used as a data structure for the running of the Viterbi algorithm. This particular table has a number of columns equal to length of the observation sequence plus 1, which corresponds to epsilon, and this particular column with epsilon indicates what the first state of the system is. The system goes to S1 with probability 1.0. However, if both the states are possible right at the beginning, then we will distribute this probability between the 2 rows here. Let us understand the next set of columns. Here the rows indicate the ending state, the sequences which end in that particular state. For example, this particular row is for all those sequences which end in state S1, this is for all those sequences which end in state S2. Now, when A1 comes as a symbol, then we have the transition probability of 0.1 and 0.2. Now, we record at every cell a tuple. Okay. So, this tuple is the record of all the accumulated probability of sequences ending in that particular state. So, the sequences which can end in state S1 are 2 in number, coming from a previous S1 or a previous S2. So, we see here the probability of those sequences are 1.0 into 0.1 and 0.0 into 0.2. So, 0.0 comes from this particular cell here. 0.0 is the probability of the sequence ending in S2 when epsilon is in, that means when no symbol is in. So, when we advance that particular node, we have to multiply the probability of the transition with 0.0 and we get 0.0 here. Similarly, we get 1.0 into 0.1 here and this is bold faced. The meaning of these tuple is that from S 1 we get a sequence ending in S 2 with probability value of 0.3 and from S 2 we get a sequence ending in S 2 with probability 0.0. This is this 0.0. All right. The next symbol makes things much clearer. In the next symbol, we find that a tuple has 0.02 and 0.09. The tuple here has 0.06 and 0.04. This 0.09 comes from the accumulated probability 0.3 multiplied by the transition probability of S 1 to S 2 or rather S 2 to S 1 on the symbol A 2. Okay. And this is the winner probability of the sequences ending in S 1. Similarly, the winner probability here is 0.06 of the sequences ending in S 2. In the next symbol A 1, the tuple is 0.009 and 0.012. This is the winner probability. Here this is the winner probability. Finally, 0.0081 is the winner probability here. Now, from this table we can work backwards and recover the state sequence. So, final state as we see from the bold faced portion here is S 1, the state sequence is ending in S 1 and it came from S 2 because this is the second tuple here, it came from S 2. So, we come here, this is the bold faced number, this is the first component of the tuple. So, this must have come from S 1. So, we go to this cell. Now, the bold faced number is this, which is the second component. So, it must have come from S 2. So, we come here, okay, and then the sequence comes out to be equal to S 1 to S 2 to S 1 to S 2 to S 1. So, this is the way the computation proceeds with the observation sequence, and after the computation is over, we can recover from the data structure the whole state sequence. The bold faced values in each cell shows the sequence probability ending in that state. Going backward from final winner sequence, which ends in states S 2 indicated by the second tuple, we recover the sequence. So, this particular tabular representation, which is the data structure corresponding to the working of the Viterbi algorithm, is very convenient to store the computation and also to finally recover the path. So, this gives rise to the algorithm for Viterbi, and it is the version that appears in James Allen Natural Language Understanding 2nd edition, Benjamin Cummins Publishers 1995. So, what is given to the algorithm is the HMM, which means we are given the start state S 1, the alphabet A 1, A 2, A p, which is the observation symbols, the set of states S 1, S 2 up to S n, the transition probabilities for various state pair and output symbol combination, and this is nothing but P S I going to S j on symbol A k, which is equal to P S j comma A k given S I. So, the probabilities of all these combinations are given to us from the transition and observation probability tables, and the output string we have been told is that A 1, A 2 up to A t. We have to compute the probability of this best state sequence, which corresponds to this observation sequence. To find the most likely sequence of states C 1, C 2, C t, which produces the given output sequence, that is C 1, C 2, C t is equal to arg max over C of P c given A 1, A 2 up to A t with mu as the model. For this algorithm, we have a data structure, which is an n by t array called the sequence core to maintain the winner sequence always. N is the number of states. So, n rows and t is the length of the output sequence. So, the number of columns would be equal to t plus 1. Another n into t array called back pointer to recover the path. So, the three distinct steps in the Viterbi implementation are initialization, iteration and sequence identification. When we initialize, we make sequence store 1 equal to 1.0, that is to show that S 1 is the starting sequence, back PTR 1.1 is 0 to show that this is the first state, no state precedes this, and for 2 to n do sequence core I 1 equal to 0.0. So, we make the probability value 0 in all states other than S 1. Now, comes the iteration step for t equal to 2 to capital T do, for I equal to 1 to n do. So, this means we go over the observation sequence symbol by symbol, t equal to 2 to t, the capital T is the length of the observation sequence, and for every symbol on the observation sequence, we do an iteration over the number of states. So, this is to record the state in which the sequence is ending. So, sequence store I comma t is max of j equal to 1 to n, sequence core g comma t minus 1 into probability of S j to S I for the symbol a k. So, this essentially is multiplying the accumulated sequence probability, which is sequence core j comma t minus 1 by the transition probability from S j to S I on symbol a k. So, this particular max makes sure that we advance only k states at a particular level. Okay. So, this is the most important part of the Viterbi algorithm. We do not advance any state whose probability value is less than the winner sequence's probability value ending in a particular state. Back pointer I comma t is equal to index j, that gives the maximum of the above. It is a way of keeping the pointer to be able to recover the state sequence. Sequence identification, finally, C t equal to I, that maximizes the sequence core I comma t. For I from t minus 1 to 1 do C I equal to back PTR C I plus 1 comma I plus 1, and this produces the state sequence which has been found to be the highest probability state sequence. Now, the back pointer can be a single dimensional array, and the sequence core can be of order t square. One can compare this Viterbi search with A star and beam search, and the reason for this comparison is that both these algorithms are finding and recovering sequence. So, it will be an interesting idea to compare the nuances of the algorithms. Now, we come to an important topic called the forward and backward probability calculation. We will make use of some mathematical expressions for this case. We go back to the definition of hidden Markov model, because this will be required for forward and backward probability calculation. The set of states is S, where the number of states is equal to n. The start state is S 0 and probability of S 0 is equal to 1. Output alphabet is O, where the number of output alphabet symbols is m. The transition probabilities is a matrix A with values small a I j, state I to state j. Transition probability is given through the number a I j. Emission probabilities B is B j O k, probability of emitting or absorbing O k from the state j. Initial state probability is pi is equal to P 1, P 2, P 3, P n, and each P I is equal to probability of output symbol being epsilon and the state being S I given the state S 0. So, it is essentially capturing the probability of the system being in a particular state initially. We now define the forward probability f k comma I. The forward probability f k comma I is probability of being in a state S I having seen O1, O2, O2 up to OK. So, this is better expressed by working through the mathematical calculations. So, we are working out the forward probability. So, a diagram is useful here. We have the symbols O1, O0, O1, O2, OK minus 1, OK, OK plus 1, OM. The system starts from S 0 and goes to some state here. Let us assume the probability of the state is S or the state is S q when the symbol OK is seen, and before that the state was S p. S p to S q on symbol OK. So, the forward probability f k comma q is the probability of seeing O naught, O1, O2 up to OK and being in state S q. So, this is a joint probability which expresses the fact that we have seen the sequence O naught, O1, O2 up to OK and we are in the state S q. So, it is quite easy now to express probability of the whole output sequence O naught, O1, O2 up to OM. This is nothing but probability of O naught, O1, O2 up to OM comma S I equal to 0 to n. So, this is nothing but marginalization. So, this whole sequence probability O naught, O1, O2 up to OM is appended with a state S I, and we have to take all possible values of S I goes from 0 to n, where n is the number of states. So, this means that the final output probability or the probability of the output sequence P O naught, O1, O2 up to OM is nothing but sigma f m I equal to 0 to n. So, by using forward probability we can make use of we can find out the probability of the output sequence O 0 to OM. Now, how to efficiently get FM I? This requires us to peep into the subsequences of O naught, O1 to OM. So, we invoked this diagram once again O naught, O1, O2, OK minus 1, OK, OK plus 1, OM. And we have the state here as SP and the state here as SQ. The state here is S0, it goes to any state S1, S2, etc. So, now F k q is nothing but the probability of O1, O0, O1, O2 up to OK and SQ. So, probability O1, O2, O0, O1, O2 up to OK and SQ. So, these I can write as this is the sequence on which I am operating, and I am trying to see if I can make use of the subsequences property to compute this probability. So, this would be equal to P O naught, O1, O2 up to OK minus 1, OK, comma SQ. So, I am just dividing this sequence O1, O0, O1, O2 up to OK into two parts, O0 to OK minus 1 and OK. Now, I do marginalization and I introduce another variable O0, O1, O2 up to OK minus 1, comma SP OK SQ, where P is equal to 0 to n. So, this I am allowed to do, I am just introducing marginalization. Here is a new state which is introduced. This is SP, SP is nothing but the state previous to SQ, and having seen the sequence O0, O1, O2 up to OK minus 1, the system is in state SP. After that it sees OK and goes to state SQ. All right. So, this is the expression. Now, what I can do is that I can take up this particular term O0, O1, O2 up to OK minus 1, comma SP, comma OK, comma SQ, P goes from 0 to n. This I write as sigma P equal to 0 to n, probability of O0, O1, O2 up to OK minus 1 and the state SP into probability of OK, comma SQ given O0, O1, O2 up to OK minus 1 and SP. So, this is how the chain rule operates. I have taken out this particular part, okay, and I take this part as the conditioning entity in the next probability, which is multiplied. Now, P equal to 0 to n, this probability is familiar to us. This is nothing but f k minus 1 p, and this probability we can neglect O0 to OK minus 1, because we said that the next state and the next symbol depends only on the current state. So, okay, next state and the next symbol depends only on the current state. So, this is equal to P OK, comma SQ given SP, and the term comes out to be equal to P equal to 0 to n f k minus 1 p into probability of SP to SQ on OK. All right. So, this is the expression that we have got, and it is a recursive expression for the forward probability, giving us a recursive algorithm to compute the forward probability. So, what you have got is f k comma q is nothing but sigma f k minus 1 comma p, p is equal to 0 to n, the recursive expression. Now, from this we can draw a diagram and see how this quantity is computed. So, f k comma q is computed by f k minus 1 comma 1, f k minus 1 comma 0, f k minus 1 comma 1, f k minus 1 comma 2 and so on, f k minus 1 comma n. And on these we have the probability S0 to SQ on OK, probability of S1 to SQ on OK, and probability of Sn to SQ on OK. So, how this will be computed is as follows. We get these f values, multiply them by the transition quantity here, and sum up all these products, okay, to finally obtain f k comma q. So, f k comma q is obtained from f k minus 1 0, f k minus 1 1, f k minus 1 2 up to f k minus 1 n. So, there are these n computations of f, and each is multiplied by this transition, and finally, everything is summed up. Okay. So, we can see that at every stage we have n computations. Now, f k minus 1 0 can again be computed as follows: f k minus 2 0, f k minus 2 1, f k minus 2 2 up to f k minus 2 n. What are the probabilities on these arcs? The probability here would be p s 0 to s 0 on k minus 1th observation. This will be p s 1 to s 0 with order k minus 1 with observation k minus 1. This will be p s 2 to s 0 with symbol k minus 1, and so on. So, as we develop this tree, we will finally have a situation where we are computing f 0 0, f 0 1, f 0 2 up to f 0 n. Okay. And these are used to compute f 1 0, then f 1 1, f 1 2 up to f 1 n. All right. And these quantities, which are the boundary conditions really, these are nothing but p 0, p 1, p 2, p n, and these are nothing but initial probabilities. So, the boundary condition is the initial probabilities. Okay. These are the termination points for the recursion. So, from f 0 0, f 0 1, f 0 2, f 0 n, which in turn are the initial probabilities, we can compute f 1 0, f 1 1, f 1 2, f up to f 1 n. We can see the probability on any arc here. The probability here, for example, would be this p s n to s 2 on symbol O 1. Okay. So, this is the probability. So, this probability is known, these probability values are also known. We multiply them, and at each node we perform a sum of these lower probability values, some of these lower probability values. So, therefore, it is quite easy to see that forward probability can be computed in linear time. So, the complexity of forward probability calculation is nothing but number of states into length of observation sequence. So, number of states into length of observation sequence. We can similarly compute the backward probability, which we will see in the next class.